Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures we have been discussing the angular momentum and how we can solve this angular momentum operator in quantum mechanics. So far we have discussed that angular momentum would have three different components, Lx, Ly, Lz, and we learned how to write down the quantum mechanical operators corresponding to Lx, Ly, Lz. We also defined two new operators L plus, L minus and L square, which are shown here. What is very interesting or important in angular momentum is that the commutation relation that these operators follow. For example, Lx, Ly or Ly, Lz or Lz, Lx, these three components of the angular momentum operator, they do not commute with each other. Since they do not commute with each other, therefore, we cannot define a common complete set of eigen functions for them. On the other hand, we have this L square operator which commutes with Lx, Ly and Lz. So, therefore, we can define a common complete set of eigen functions for L square and any one of these three operators Lx, Ly and Lz. We continued our discussion by telling that let us find out the eigen functions which are simultaneously eigen functions of L square operator and Lz operator. I will briefly remind you the important assumptions that we had in our previous lecture. We defined that let psi alpha beta be an eigen function of L square operator with an eigen value of alpha square h bar square, and the same eigen function is also eigen function of Lz operator, but with an eigen value of beta h bar psi alpha beta. Now, this is how we defined that psi alpha beta be the simultaneous eigen function of L square and Lz operator. When we defined this alpha and beta, we just suggested that these are two indices, but doing some more algebra we came to this important conclusion that alpha and beta are related to each other via this relation. That means, beta has an upper bound and has a lower bound. We then defined L plus psi alpha beta, and then this function, this new function that I am getting by acting L plus operator on psi alpha beta, this function is also an eigen function of L square operator with same eigen value alpha square h bar square, and this new function L plus psi alpha beta is also an eigen function of Lz operator. However, the eigen value now is not beta h bar, rather beta plus 1 h bar. So, we see that if we define one eigen function psi alpha beta, which is the simultaneous eigen function of L square and Lz operator, the other eigen functions of L square and Lz operator can be obtained by action of L plus operator on psi alpha beta. So, action of psi L plus operator on psi alpha beta gave us psi alpha beta plus 1, and one more time if I apply L plus operator, I would get psi alpha beta plus 2 and so on and so forth. Similarly, if we apply L minus operator on psi alpha beta, I would get psi alpha beta minus 1 and so on and so forth. Then we see that in this way we can generate all other eigen functions of angular momentum operator, but we know that beta cannot go from beta values cannot go from minus infinite to plus infinite, rather this has an upper limit and a lower limit. We discussed that and we realized that this beta has a maximum value and has a minimum value. We defined that the value of beta, so the value of beta went from minus L to plus L in the step of 1. So, minus L plus 1, so on so forth, and L minus 1 and L. So, these are the possible values of beta, where the maximum value of beta is plus L and minimum value of beta is minus L. We also discussed that if we have to construct a series that will have minus L to plus L in the step of 1, this series can only be formed when L is integer or half integer. So, the maximum value of beta is given by either integer or half integer. So, therefore, all other values of beta are integer or half integer. Now, what about alpha? We also, in the course of our discussion, we also discussed that alpha square turned out to be L into L plus 1. So, what is L? L is the maximum value of beta. So, therefore, if I have a particular value of for a particular value of L, I can have a definite value of L alpha square, which is given by L into L plus 1, and the beta would vary from minus L to plus L in the step of 1. Now, together, so instead of writing now my eigen function as psi alpha beta, I can say, I can rename them. For example, I would tell that since maximum value of beta is L and alpha is uniquely determined by the value of L. So, therefore, I give this notation here psi L instead of alpha, and for beta, since for a given value of L I can have many different values of beta. So, I am calling them as M, where M goes from minus L to plus L. So, these are generic way to write the eigen functions of eigen functions of the angular momentum operator psi L M. Please note here M, the value of M is actually determined by the value of L. So, therefore, in some cases you would also write a index in the subscript of M calling L, that means this value of M is coming because of this L. So, when I have this as the eigen function psi L M or psi L M L, I would see what would I get when I apply L square operator on the eigen function of angular momentum operator psi L M L. I know this would be alpha square h bar square, this is how it defined, but alpha square is L into L plus 1. So, this is what I get as and what about Lz? Action of Lz on this function psi L M L gives me only this M L h bar psi L M L. So, now what we have defined is that the eigen function of angular momentum operator are not infinite number of eigen functions, rather for a given value of L, I have 2L plus 1 number of eigen functions. We will discuss this part a little more. For example, let us say our L is 0. When L is 0, the possible values of M goes from minus L to plus L in the step of 1. So, therefore, I have only one possible value of M and that is 0. So, the eigen function that I have obtained is psi 0 0. When L is 1, M can go from minus L to plus L in the step of 1. So, M can be minus 1, 0 or plus 1. So, in that case the three eigen functions that I get are psi 1 minus 1, psi 1 0, psi 1 plus 1. So, 1 1, 1 0, 1 minus 1. So, these are the three eigen functions of angular momentum operator when L is 1. Similarly, when L is 2, I would have M as minus 2, minus 1, 0, plus 1, plus 2 and so on. So, these are the 5 possible values of M that are allowed for given value of L. But we also know that L can be either integer or it can be half integer. Suppose we take a half integer value of L, call it 0.5. What are the m values? M values are from minus L to plus L in the step of 1. So, m is minus 0.5 or plus 0.5. How would we write it? We will write it as psi half minus half, psi half plus half. So, this the first index indicates the value of L, the second index indicates the value of m corresponding to that L. Similarly, if I consider L as 1.5 or 3 by 2, my m values will be minus 3 by 2, minus half, plus half and plus 3 by 2. So, the wave functions that I would have are psi 3 by 2, minus 3 by 2, psi 3 by 2, minus half, psi 3 by 2 plus half and finally, psi 3 by 2 plus 3 by 2. So, I see that when L is 3 by 2, I have 4 different angular momentum eigenfunctions. You see I am getting 2L plus 1, 2L plus 1 when L is 3 by 2 is 4. When L is half, 2L plus 1 is 2. So, therefore, I am getting 2 eigenfunctions of angular momentum. When L is 2, I am getting 5 angular momentum eigenfunctions. When L is 1, I am getting 3 eigenfunctions of angular momentum operator. So, now what we see is that we have different eigenfunctions coming from different values of L. Please appreciate here the use of ML as the second index instead of M. Please see here, I can have M as 0 when L is 0, or I can have M is 0 when L is 1, or I also can have M equals 0 when L is 2. So, these 3 different values of M when they are actually 0, they are different functions. How are they different? Even if their M index, the second index is same 0, their first index, the L, is different. So, therefore, to distinguish them, psi L ML is more appropriate definition than psi L M, because in this case we are defining that this particular value of M is dependent on this particular on the given value of L. Now, another thing that we see is that instead of having infinite number of eigenfunctions for a given value of L, I am having a finite number of eigenfunctions. How do I represent them? The way we represent these eigenfunctions are the following. I draw this z axis, I define my origin here. From here, I define my L vector, L operator. So, this is my z axis. If this is my L operator, please remember that this angular momentum is actually a vector operator. So, this is a quantum mechanical operator, but it is also a vector. So, for a given value of L, I know that it has 3 components, Lx, Ly and Lz. But since Lx, Ly, Lz do not commute with each other, so we cannot simultaneously define them. So, we have chosen to define only L square and Lz, one of the 3 components of L, Lx, Ly, Lz, we chose only Lz. So, therefore, I am defining my Lz z axis over here. If I make a projection of this L vector operator onto the z axis, I see here this would be the eigenvalue corresponding to Lz operator. What would this be? So, this one, what is the eigenvalue corresponding to the Lz operator? That is mh bar. And what is this? This is the magnitude of this L vector, which can be given as L into L plus 1 under square root h bar. Please remember, this square root is coming because instead of L square we are using this L here. So, therefore, this square root is appearing here, and instead of h bar square I am getting only h. So, now what has happened is that this way of orienting this L vector, the this state of the angular momentum has two definite values. What? One is its L square expectation value is L into L plus 1 h bar square, its Lz expectation value is m h bar. So, this is one possible eigenfunctions of angular momentum operator. What are the other ones? For example, I can, instead of drawing this vector L in this way, I can draw it in this way. In this way, the magnitude of this vector still remains same. I am making it same, but when I make the projection to z axis, I would see that instead of plus m h, I am getting minus m h bar. So, now this is another state or eigenfunction of the angular momentum operator. So, if I am considering L as, let us say, plus 1, L is plus 1, then I will have 3 different m values, minus 1, 0, plus 1 corresponding to m values. So, in this case what I have done is that there is one here, the other projection is here, the third one I can draw it just the third one I am drawing over here. So, that the projection of this vector onto z axis is 0. Now, you see that this L vector makes an angle theta with the z axis, where this cos theta I can give as m divided by L into L plus 1 under square root. Here this L vector also makes another the angle theta, and here in this case the L vector makes an angle of 0. So, I can say that this L vector, the angular momentum, could actually be any, if I draw the all possible values of L, this would be that any point along this curve would satisfy the L vector, but quantum mechanically we know that these states are quantized. I cannot imagine any possible angle of theta, that means here theta can go from 0 when the L vector is on this point, and when L vector is on this point the theta is 180. So, between 0 and 180 I can of course imagine many values of theta, but quantum mechanically all these states are not feasible, only a certain number of states that are acceptable, and in case of L is, when L is 1, there exist only 3 different states or 3 different orientations of L that are quantum mechanically allowed. So, what are they? One is over here when ML is plus 1, another is here when ML is 0, the third one is here when ML is minus 1. So, this is psi 1 1, this is psi 1 0, this is psi 1 minus 1. These are the 3 eigenfunctions, 3 angular momentum eigenfunctions for L equals 1. How would I go from this eigenfunction to this eigenfunction? I will simply apply an L plus operator. The step up operator will take me from 1 minus 1 to 1 0, and one more time if I apply step up operator I can go to 1 from 1 0 to 1 1, or else I can also come down from 1 1 to 1 0 or 1 0 to 1 minus 1 by using step down operator. In this way what you see is that instead of having n number of eigenfunctions, I have only a finite number of eigenfunctions, and this way of quantization is known as, is called space quantization. For this is for L equals 1. If you imagine this the same plot for L equals 2, then of course you will have 5 different projections. So, this will be 2 psi 2 2, psi 2 1, psi 2 0, psi 2 minus 1, psi 2 minus 2. And what are the, so this is my z axis. So, if I make the projection to the z axis, so this is 2 h bar, this is h bar, this is minus h bar, this is minus 2 h bar, and this is 0. So, now I see these are the 5 different eigen functions of angular momentum when I go from when I consider L equals 2. When L equals 0.5, when L is 0.5, I simply have 2 possible orientations. This is my z axis, this is 0, what is this value? This is plus half h bar, this is minus half h bar. So, different particles or different particles would have different angular momentum. So, one thing we would introduce now and we will come back to later is when L is equal to 0.5, this particular angular momentum is observed as electron spin. So, electron spin has an angular momentum of 0.5, and since L is 0.5, it has 2 eigen functions corresponding to this angular momentum. What are they? They are minus 0.5 h bar or plus 0.5 h bar. So, these are the 2 spin projections that we have. One of them we call alpha spin, another we call beta spin or up spin or down spin. So, these are the 2 different spin orientation for electron spin. And why do we have only 2? Because electron has a spin angular momentum of 0.5. If you have a particle whose spin angular momentum is instead of 0.5 would be 1 or 2, you would also have 2L plus 1 number of different spin functions for that particle. But electron, by the virtue of having spin equals 0, spin angular momentum as 0.5, has only got 2 states, and we call them as alpha spin or beta spin or up spin and down spin. One final thing that we must remember in this discussion is that here when I have defined L square and Lz, these are the 2 well defined operators. That means the eigen functions, the state functions are simultaneous eigen functions of L square and Lz operator. So, when I make measurements, I can get precise value of L square and Lz operators alone. What about Lx and Ly? I actually cannot obtain any information about precise information about Lx and Ly, because I am defining my state function as an eigen function of Lz operator. So, therefore, it is not an eigen function of Lx or Ly operator, and I have some uncertainty in measurement of Lx and Ly. To show that, how we represent is that this angular momentum vector operator, we can define it as something that precesses around this z axis. So that the Lx and Ly are not well defined quantities, rather they will have some values at some, so that there is some uncertainty in measurement of Lx and Ly. So, this is how we define. So, when I define L operator, I see that this this angular momentum operator precesses around the z axis with a definite value of L square eigenvalue and with a definite value of Lz eigenvalue, whereas Lx and Ly determination would have some uncertainty in them. So, we discussed about the angular momentum eigen functions, or rather how many different eigen functions are there. But so far we have not discussed what are the functional forms of these eigen functions. That is what we are going to do next, but before that, before going to discuss that, we would introduce something else, that is a new coordinate system. So far we defined our operator Lx, Ly, Lz, and they were defined in Cartesian coordinates. But the angular momentum comes into picture when we have a particle which shows a circular motion, and in such a case, when we have a system which shows circular motion, in such a case it is convenient if we convert our coordinate system from the Cartesian coordinate to another coordinate system that we call spherical coordinates. So, we define these spherical coordinates here. For example, if you see, if I have x, y, z, the Cartesian system over here, a point in this Cartesian space shown here has a dimension has a coordinate of x, y, z. Instead of defining in x, y, z, we are defining new coordinate system r, theta and phi. R is the distance from the origin to the point in the 3D space. So, this distance is r. Theta is the angle that this r vector makes with the z axis, and phi is the angle that x axis makes with this point with this vector. And how do I get this vector? When I make a projection of this point onto the xy plane, I get this point, and the vector that joins the origin to this point, the vector that it makes the angle with x axis, that angle we call phi. So, when you see this this coordinate system, we call it spherical coordinates, because for a given value of r, if you take all possible values of theta and phi and construct the geometric shape that is coming out, you will actually get a sphere. So, what are the values of r, theta, what are the possible values of r, theta, phi? So, you see r can be 0 to infinite, it goes from 0 to infinite. So, this would simply show the size of the sphere. Theta on the other hand goes from 0 to pi, and phi would go from 0 to 2 pi. We have looked at this spherical coordinate system, and what we will do in the next class, we will discuss that how we can convert our system from Cartesian system to spherical coordinates and vice versa, and how we can define our angular momentum operators instead of Cartesian coordinate, how can we define them in spherical polar coordinates. These are the things that we will discuss in our next class. Thank you for your attention.